So, all right, so now we can jump into our second discussion. Okay, so, either of you would like to go first now? Let's see. Maybe has to. Okay. So if he pops up, we can.
Yeah, this is actually not a microphone, so you.
Oh,
can
okay.
just go ahead.
The microphone's up there.
So with all, you want me to go first?
Sure.
Okay. So with all the topics that have been raised today in connection with Alex's pioneering work, it's hard to make a sub-selection for a few comments. But let me take the jumping off point to be what was mentioned earlier about the 1975 conference in Tucson, which was labeled the Tucson Crisis. How many people here were at the 1975 Tucson conference? No, come on, you weren't there. You weren't even born. Okay, so I'm the only one, I guess, in the audience that the 1975 meeting. And there's a connection here with discussions about USDB, because I'd like to recall at that point in time, what the main thought was going into the meeting was, oh, we have Bruckner theory, we have Bruckner beta Goldstone perturbation theory. All we have to do is work a little harder. Kuhl and Brown showed us it could work. If they just did a few calculations, maybe we could do those calculations better. Well, that's where the problem went off the tracks. The train went off the tracks when you tried to do the calculations better than Kuhl and Brown. And what did that mean? You tried to do higher order perturbation theory. That was Barrett and Kearson. They did third order perturbation theory following the second order perturbation theory, Bruckner beta Goldstone diagrams that Kuhl and Brown had done. And lo and behold, third order perturbation theory was as large or larger than second order perturbation theory. Major problem. We don't have a convergent theory. Okay. Then Weidenmuller and Lee showed that the problem was intruder states. Perturbation theory does not converge if there's states outside your space that come down into the region of the physics you're trying to describe. It totally spoils convergence. The third problem that was discovered is separate from those two, was a problem that I had discovered with Peter Sauer and Chunhua Wang, which is the problem is if you try to improve Kuhl and Brown by expanding the intermediate state sums from being only 2 H bar omega excitations, then those 4 H bar omega, 6, 8, 10, 12, they also don't converge. So you have multiple problems with Bruckner beta Goldstone perturbation theory. So everybody is totally destroyed. Very sad day. End of the conference comes. We've all wasted our time. We're doing calculations that are at a very bad theory. So you could, and it was correct. People went away discouraged, and other people, those of us who had a career ahead of us, thought of it as perhaps an opportunity. And I got together with my collaborator, Bruce Barrett, and we said, hey, you know, things like SD shell effective interactions seem to work. You still have two-body effective interactions that they, you know, you had P shell interactions, Cohen and Kurath, you had some early SD shell interactions. And of course, as time goes on, there's even better sets of 63 matrix elements for the SD shell that work and give you beautiful spectroscopy. So in a sense, we don't have the right theory, but the existence is provable or demonstratable by the successful phenomenology. You have the FP shell work, you know, the work that Taka and others have been involved with, GXPF1 and so forth. So there's good physics to be learned, but we just don't know how to do it yet. So a subset of the community took up that challenge and said, we got to get rid of the core. We can't do Bruckner beta Goldstone perturbation theory with a core. This is just not going to work. We proved that. So then comes about 15 years, 20 years of trying different things. We were limited by computer power. So we tried moment methods. We tried some other approaches. It had to be non-perturbative. That's the other rule. So eventually everything came together for us with the no-core shell model. Peter Navratil summarized that nicely earlier today. But then we're still very far from USDB or GXPS1 or any of the other Cohen-Kurath P-shell effective interactions. We still have a long way to go. Well, the beauty is in the last, say, 5, 6, 7, 8 years ago or so, you have IMSRG showing the way. You have a version of the no-core shell model with a core. I don't know what you really should call that, but you can put the core back. Once you have non-perturbative solutions, you can recalculate the effective interactions for P shell, SD shell, PF shell in principle, and that's underway. We still have a long way to go, and there are a lot of problems. And you heard about some of the successes of the IMSRG. Multi-particle, multi-hole configurations are important. There's a lot of intruder physics still lurking there. Sums over intermediate states. All the original physics problems are still underlying what you have to do, but you have to do it non-perturbative. That's all
A question occurred to me there, just because you were at that meeting. People were optimistic because things looked so good with the Cool Brown before, and I mean, you look in textbooks from that era, they have that cool brown plot and everything looks beautiful. Is it just tragic misfortune that it agreed so well with experiment, or do you think there was also kind of psychological effects going on as well?
It was their brilliance. They knew when to stop.
They knew when to stop. And that was exactly what was said, you know, but they did the calculations they could do. The other thing is there could be a coincidence here that the computers were very limited. The calculations that Tom Kuo did was a huge undertaking. And give them a lot of credit. They did a great calculation for the technology they had at the time. And it seemed to agree pretty darn well. So they were very excited. And I well remember after the appearance of our paper, walking with Jerry Brown one day. I was at Brookhaven as a scientist at the time. We were walking to lunch and Jerry Brown looks over at me and says, "Barry, you know you're wrong." And I said, "Where?" "Oh, it's not possible," he said, you know, this slow convergence of intermediate state summation. But he didn't read the paper. And I went on to describe to him, if you study the role of the tensor force and the detailed properties of the intermediate momentum transfer tensor force characteristic, it stares you in the face. You just take your core polarization diagram, do some simple geometrical factors, and you don't see any convergence right away with the tensor force. So we tracked that all down in the original paper. So, but that means anybody who's doing the non-perturbative calculation should still be aware of that, because we have to keep that physics. There's transfers up to 1.5, even perhaps 2 inverse Fermis that have to be accounted for with our current chiral effective field theory interactions. They all have strong tensor force components.
Maybe I'll sort of pick up where James left off with, they started to come up with ways of solving the problems, but we still have a lot of issues that need to be resolved. But nowadays we have an incredible tool chest in terms of all of the different methods that we heard about and others that we can sort of try to use to learn and compare to each other and probe to see, where do some methods do really well? Where do some methods fail? Do we understand why some fail and some don't? We have other techniques for trying to probe the underlying wave functions like symmetry decompositions or applying simple models like rotational picture to sort of see where simple intuition things evolve as we go to heavier systems, how do they evolve as we go to neutron or proton rich versus just going up the n equals z line. We can use all of this to sort of guide us in terms of looking for what are the relevant degrees of freedom and the things that we really need to include in our theories as we try to push further up the nuclear chart to heavier systems.
So one point I would like to, like one thought I would share with you guys. So Parker gave a talk this morning and emphasized the value of sharing the code. With that, the shell model became very popular. So Alex, do you have a number, how many times your code was downloaded?
In a way, but what happens is it gets downloaded, then that person downloads it.
Yeah.
So I have no idea.
Lower bound.
Is there anyone in this room who has not downloaded it?
I mean, I know the citations, but I'm not sure that's, but I think that's what I pushed at the beginning. If I could do something, I wanted somebody else to be able to do it, if they had a certain level of understanding. It's still true that people download it and they really have no idea what they're doing, and that's, you can do anything you want. But I think for the most part, it's been used for in good ways.
So do you think like, if something like emulator can be, get to the level that people don't really need to understand?
A little bit like these codes, you don't have to understand how all that's being crunched in the middle, but you do have to understand what it means: Hamiltonian, model space, observables. Okay. I mean, I would, I know there are other codes out there, but I put some effort into what I call wrapping the code into something relatively easy to use. Doc, I don't know if you appreciated that or.
I don't know how many times.
Yeah, as Christian mentioned in his talk, right? So actually several talks today already mentioned emulators. I think in some sense, on that aspect, the reason is because we see that the future, that emulator can play similar roles as a wrapper around not just shell model calculation, but very expensive calculations. And Christian mentioned that the emulator itself is very simple, like hundreds of lines of code, hopefully. So then the issue is, okay, people can use it, and meaning that they can understand your calculation, how it works, the predictions in the parameter space, without really understanding the physics behind it, without spending a lot of computing resources. So my concern, just after hearing about your answer is that kind of blindness, is that helpful or not? That just completely don't know what is behind the code, and then they will use it.
Depends what you want out of it. If you want to improve the code, then of course you have to. Yeah. But if you just want to understand some observables, and you believe that that code is giving you the right answer for what you put in, then it's very useful. I can see it. I can see such codes or any other codes being wrapped around other things like emulators or whatever, as long as they're well, documented. And I these days I think of things as being more modular. I used to write, actually my code maybe 30,000 lines long, and there's a problem. I'm the only one in the world that knows more or less what those 30,000 lines mean. But making them more modular, like this little bit just does the beta decay part. I think it's important.
I think it inspires me that it's also important to make sure that people know that this didn't end your career to make this code that you worked on available. Because I think there's a lot of people out there who work on codes that are 30, 40, 50,000 lines, and they are very hesitant to share them because they've done all this work to build this thing,
Well,
and they're worried.
I used to worry about things like that. Now I don't so much, but I realize that even if generally I don't give out the code, I give out some executables. And I love to do programming on a Windows machine, because that's how anyway, it's so easy. But most other people don't. So I always have to worry about the other edges of it, like that. But I've never given out the code, and now I realize it doesn't make much difference, because I don't think anybody else could understand. So now I should just, at this point, I should put it there, just so it's not just on my computer, but it's someplace else.
I think like because of this availability of the calculation, right, to people, like in particular experiments, I see so many cases of people quote like anecdotal things, or they interact with you because they can get calculation from you. And because of that, I think in the future, I think maybe emulators will be helpful in that aspect. Like even the experiments, they can get some information out of the calculation without running. You can think about emulator literally as a table, summarizing all the possible results you can get in experiment space. You can say you can get it in the list.
Yeah, as long as each part of the thing is documented, you have your simulated part, you understand what that's doing. And then what is it using to, what's its source of numbers? Does it come down to a set of 2 by matrix element, or is it something else?
What would be the most crazy application of your? I just imagine, because I always think, okay, as soon as you make something acceptable to people, you can come up with creative ways to use it, like out of your imagination, something like that.
You mean crazy by bad? Good. Oh, good crazy. Wow. I realize that what Mitaka is doing is quite a bit different and much more advanced. I don't know if his code is available to us. So we can calculate. No? I think we've talked about that. Yes. I think it's a good learning tool. I mean, I've often used it just as a matter of teaching courses, but I never always build up to it. So it's always just the end part of the course. I always, first of all, go through all the equations that it takes to make such a. When George Birch was here for our meeting in the spring, we were talking about what do people understand. And we were talking about such simple things as 6J symbols. Back when we started in the 50s, there was a book. You actually had to look up the value of a 6J symbol in a book and write it out. And then there's, of course, we all have codes. That was done in the late 60s and 70s. But now it's like nobody needs to know anymore. It's all just part of the, it's the number crunching inside the code. I don't know if you really don't need to know. I think you do actually, in many situations.
Like you compress the knowledge into your subconscious.
Well,
The trouble with that book was usually somebody had it out of the library and hadn't signed for it. We get in their office. Oh, you're wrong.
well, that would have been me. I think.
We could come back to those 6J symbols. What people need to know is how angular momenta couple. I mean, to build a physical picture of that in your mind. And this is hard for most people. But that's what is needed.
And that's true for any groups above SU2, SU3, SU4.
Does a mathematician do anything with that? About the situation with understanding groups?
Maybe shift, or maybe return to what James was talking about. There's because this last section was about ab initio calculations. think of anything specifically that Avenue can learn from what has been done, shell model and phenomenology more broadly, the insights that can really help point to what we should do.
For sure. I like to think of it, as I mentioned, as the demonstration that a two-body effective interaction can work exceptionally well in the SD shell. 63 matrix elements, they do a spectacular job. So the question is, what's the correct theory, or what's the best theory that produces USDB, or something as competitive as it is? It's helpful to remember that those 63 numbers are not necessarily unique numbers. I think Alex many years ago provided the eigenvectors of the correlation matrix, which tell you the equation to which the numbers are determined. And basically there was something like 7 or 8 or 9 linear combinations that are well determined, and the rest have a lot of uncertainty. Is that USDB or an earlier?
Well, they all have something like that, but what's so important to us is to have some good initial starting point. And that was always, for example, that was your pro-grounded. And then we changed it a little bit. Not all 53, but we changed a few, maybe 30. But you've got to know something about the others, because the others have an effect on other things just besides energy.
A good reference starting point.
Yes, so I'm very happy these days because now we have better starting points. Now, people get upset with me when I have yet another and I promise not to do that anymore. I think it's important for heavier nuclei to have better starting. And that's what we're thinking about.
A lot of our intuition in terms of what we see in our calculations and trying to understand what's comes from the shell model. Like we talk about intruder states, that to me is very much a shell model concept. And it doesn't make any sense to me outside of the context of the shell model. And if we want to try and understand possibly what we're seeing, or is it consistent? Does it actually look like the physics? Well, how do we talk about it? All we have is numbers. So we need things like the shell model, or these somewhat simpler pictures that are more intuitive to understand that.
Well, the word intruder is a relative statement. Because it depends on the starting point in your model space. So back, for example, back in the 60s, we worked on the Sept and intruders from the P3 halves orbit. Okay, so we just keep expanding, and so the intruders go away because they get embedded into the calculation. But there's still big areas where I don't think anybody can do a good job. The one I always, every time Bruce Barrett gives a talk, I always ask him, what do you get for the intruder energy in 018? You know, it's the four particle to whole state, which comes at around 3 MeV. And most people still don't have, you still don't have that.
If you go to 016, you've below 13 MeV, you have all the way up to 5H per omega states that are explicit in the spectrum. So if you go to F18, you've got 0, 1, and 2H per omega below 1.7 MeV.
That's our understanding, but I like to see an IMSRG type calculation. That's that as an output rather than our just inside our heads.
This is the homework assignment for right now.
I mean, am I saying the right thing?
I actually, Heiko would like to say something.
I'm also still. So I think one of the interesting things to try is to see whether we can build collectivity into the shell model interaction. You know, what you would call high particle, high hold states. By doing, for instance, something like an evolution using a GCM reference state to prepare the operator basis in which we run the flow, and then we develop an interaction that has that collective physics built in. So is that going to mean that our intruder states will be starting roughly where they're supposed to be? I mean, what you would call an intruder state, and are they not going to move a lot anymore as a result or not? But this, I think this is stuff that actually in an IMSLG framework, you can actually explore. We know how to do that. We haven't done it, but we know now how to do this. And this is something we can start and tackle in the next several years. I mean, it's not going to be a super quick thing. But I think with previous methods, we didn't quite have that flexibility that this can offer us.
There's a lot built into these recent and symplectic truncations. Because you are allowing yourself the quadrupole and collectivity to be connected between 2 per omega, and you don't need an effective charge. That's a big step. So that can go far. I think there's a lot more to do there. I just heard today that Thomas Papenbrock is doing, he starts with a deformed reference state. And that seems to help him. I don't know if
It does.
Yes.
Yeah, they're behind you.
So I think there's lots of avenues out there that need to continue to be explored, but you're always stuck with the computational.
You've got to get your 2-particle, 2-hole, 4-particle, 4-hole and states all in the right order too, because as the old Brown and Green model shows, the phasing of these really helps on your BV2s and so on. So you've got to get them all in the right relative order.
Well, that's what
That's in addition to your 1-particle, 1-hole excitations through 2H bromide.
Okay, well, I think that's towards the end of the session here. And so we have another session back to back. Let's take it on.
Panel. Panel, Chloe, Constance, Yanjo, Kyle went.
Well, that's ground.
Christian, are you there as well? Let's see. All right, so this panel is about the future. All right, so lots of things to talk about in terms of connecting with communities, in terms of building the workforce, in terms of transferring knowledge, in terms of preserving codes, documenting codes, sharing knowledge, insights, all that. So if you have any thoughts on what, another thing is also including emerging technologies, things that maybe we had not had before that could improve it. But if you have some ideas on that, go ahead. Maybe if you just like raise your hand and then I'll call on you.
There's a hand up on the screen.
No, that's your.
So I think I'll start with a little bit answer. A former partner of mine wants to give a talk here at FRIB, and she's a astrophysicist, knows first nuclear physics, showed up several hours early for where she was supposed to arrive here. And Alex took her into his office and actually talked about nuclear physics and the fundamentals of it for several hours, just out of the kindness of his heart and the work of teaching young people about nuclear physics. And I think that type of attitude and that type of just behavior is absolutely critical to building a broad, robust workforce that both understands nuclear physics as experts, as well as understands how to use it in their own relevant domains. And I think that's just actually a really fantastic thing and something we should really applaud you for.
In the interest of sharing personal anecdotes. Nevertheless, when I was a grad student, I really appreciated how in your code was always public, interactions derived, always the matrix elements were always made available. And it's come to the point where I helped create an interaction. I was not able to have the matrix element. And from what people tell me, the best way to get the matrix elements is contact you. After some years. So in that sense of training the future workforce, making codes available, making science inclusive in general, it really helped me quite a bit. I feel it helps quite a few other people as well. And well, I guess we'll be going back first.
I think not just in terms of sharing code, but in terms of writing code, it's important that people get credit for that because we get more you know, brownie points for publications than necessarily code that other people use. And I think we need to make sure we value that and value well-written code, well-supported code, and so forth. We have a lot of tools now, like GitHub for sharing, and we've seen stuff. I know Ragnar put some of this stuff on there. And we can continue to do that and continue to really have standards that we should have well-written manuals, lots of examples from these codes. And so forth. There is always the danger, as was mentioned earlier, of someone, you know, misusing it. John and I at FISRFC always bemoan what we call turn the crank papers, where there are papers where people will download. None of you, of course, no one here, but there are people who will download codes and just crank out stuff and then just try to submit a big table as a paper. And what I always say is, what physics did we learn from that? What did we learn? So there's a question about emulators earlier, is like, well, we want more than just an answer. What did we learn? What insight do we learn? So not sure how I got to there, but so let me give credit to somebody. Maybe not everyone knows. I was lucky when I went to Oxford in the late 70s. I met somebody, Bill Ray. And he was a genius at what I call making the heart of these codes, meaning getting all these multiple words and OpenMP and all these things that make the code fast. And so all the codes I have used, he has written that what I call the heart. And then I take that heart and I make things out of it that make it more useful. Anyway, I just want to say that Bill Ray, he died a couple years ago. He was a genius at that.
He was actually an experimentalist when I was at Oxford, right not long before you.
So I guess the message is that some people are really good at certain things. And it takes teamwork in that sense. You know, this person does something good and then this other person does something, uses it, and then experimentalists use it. So it's seldom one person, and it's never one person. I do think it's useful when you're writing code to try to, have some pity on future users. So I always try to write what I don't call it user friendly, but I just call it less user unfriendly code.
Especially since usually you're the user 6 months from now.
Yeah, well, this is what I always tell my students is like, I know you think you don't need to document it now because you'll always remember it, but even 6 months from now, and then they come to me and say, Professor Johnson, you're absolutely right. I looked at it and I wrote it and I have no idea how to use it. So, they learned the hard, they learned that I was right to tell them. Should do that. I'll try to take that. The balance between writing a great documented code and then also having a code that actually works. And often you can write a good code that's completely documented and then it's lost. Some other code comes along and You know, and it does the same thing better, or people just don't get it. I mean, it's gone, so.
So I want to echo what Kai Costas and Calvin have said, and there is, I think, to teach the next generation, there is the importance of sharing code, documenting code, make it user-friendly. But at least for me, so that's linked to my personal experience, is also the fact of meeting people and explaining to them at schools. So in my case, so I feel a bit like an imposter because I'm a reaction theorist at first, and somehow I'm ending up talking in a structure workshop. But the first time I met Alex, and he doesn't remember because I was one of the 100 students at this school, he taught us about Shell model. Didn't know anything. He was a second year graduate student in Spain. And also you made us install your code and try some model spaces. I remember back then I felt like many of the words were jargonic, like model space for me was using for my calculation. And we were moving from shell to shell, and I was like SD, PF, was a bit lost. But still during this week, I learned a lot, and I think you can have the best paper, the best code, the best documentation. At some point, you need to actually have interaction with the students. And in this case, it was because you were there teaching shell model and explaining how to use your code and style your code that I was able to get a bit of a sense of how we can get nuclear structure prediction using the shell model. And later on, I actually did a no-code shell model calculation, and was also through the bias, not the bias, through a school. So this is how I ended up doing more nuclear structure. So I really think that summer school are the ingredient to motivate students to learn, but also to learn efficiently. Sorry. So yeah, thanks for giving me a taste of nuclear shell model when I was even pure reactor theory.
Let me say something obvious. There's been many generations of codes. And the very first thing we always check is, does this code give the same answer as the previous one?
Seems reasonable.
And that doesn't always work. They're quite complicated. There's so many ways to go wrong, like we saw today. Just got one little index wrong. You know, it would be a disaster if you only had one version of the code and you randomly took out one letter someplace. Can you imagine how you would fix that? You didn't have any backup version or anything like that? Impossible.
Yeah, the difference between science and art.
Okay, so also I need to thank Alex. Maybe I'm the one of the youngest guy in this room. Maybe I'm the guy who have the shortest overlap with you. The first conversation with you happened several months ago. But I know you, at least your name, since my first year of my graduate as a graduate student, and learned quite a lot from your lecture notes. It's quite inspiration. And also just 3 weeks ago, when I make a phone call to my parents and discuss about you, that how you job at your age actually itself is an inspiration, at least for myself and our generation.
So you talk to your parents in what language?
In Chinese. Okay.
How do you say my name?
It's just Alex. Okay, so about the codes, I think we know a lot of on the market. Since I was a graduate student, I heard the name of it, but usually it's quite hard for me to find maybe I'm lack of knowledge. There maybe have some website to list it with this morning and resource team. Maybe if it is possible, could we make some website as a dictionary of all the current codes and with some corresponding people? If the code is available, open source, we can put some link of the GitHub. Otherwise, we can contact that people. Also, maybe there exists something like that already. We can make some improvement. And also, I think for the users, potential users, for example, the graduate student and also our experimental gap between the codes and the users, maybe it's just we discussed before. the run script or the inputs. So if we can do more on that kind of website to just have some selection of which nuclear and what kind of interaction you want to use, then it can generate a kind of script for that kind of code differently. That could be quite helpful. And for the future, I think we may meet some difficulty to keep pace with the development of the current supercomputer. So, for example, nowadays, scale computer, which was almost accelerated by the GPU devices, which is not natural for our current computational structure of the nuclear model, like the large scale sparse matrix organization. So it's a challenge. I don't know how to do it. It may have, we may need some mathematic help. So I think because with that kind of superpowered machines, I believe a lot of difficulties in our calculation, like the nuclear shell model, I believe it can have a much more ability of calculating the nuclear observables.
Let me comment. I had thought about with GPUs, and I've had people ask me about that. And if I were younger, maybe I could do something about it. But I think it's the kind of thing that you kind of have to build into the code from the very beginning. You can't just take an old thing and say, I'm going to do that with my 1,000 GPUs on my laptop. Right? So things like that, you have an old code, but you have a new kind of technology, and then you have to write new code.
Chat GPT do that?
Yeah,
You do it well.
Actually, to my experience, when I'm making the GPU code, I just, like you said, I read it from the very beginning to how to construct, how to make use of the device, which is a key point.
Right.
You can run the code on the GPU supercomputer, but it's quite hard to make use of it. So that's a key point.
And I would think they would make that easier. I would have think over the years, they're going to make the use of GPU easier for us normal people to.
Patrick.
So one thing that I wanted to bring up that's sort of related to what you were talking about, and actually just a few weeks ago, I was visiting Iowa State and was talking with Peter Maris about this. So it's interesting in nuclear physics, at least in nuclear theory, I think we're one of the few fields where most people write their own code. So like if you look at condensed matter, the condensed matter theorists are not generally the ones who are writing the condensed matter theory codes. In fact, a lot of times people are using some package which has an entire team dedicated to developing it. And it's a different culture, it's a very different field and all of that. But it's one of these things where I think that sometimes in physics we've struggled a little bit when there are new technologies because we don't have this efficient, we don't necessarily have ready access and collaborations with all of the, software engineers or applied mathematicians. Some people, and we try and do this, but there's a sort of element of, is there a way or something that we should think about where, people can really specialize in working on developing codes in a way that, sort of specialization lets people be more efficient. And I'll bring up, there's an interesting, I think there's a conference in Chicago that I happen to see online where there's this growing discussion about what people call research software engineers. And this idea that, there's this sort of division of labor where it's maybe people who have formal training in a particular research area, but then go and, their job is they're going to write code and support people who are doing sort of more of the science. And so it's an interesting question about like, are there pieces of that model that are useful when we're talking about developing code?
How do you get funded for that?
That's the problem.
How do you get tenure for that?
Yeah, I think part of it also though is frankly scale. So quantum chemistry, you're going to have thousands, if not tens of thousands of people around it. And basically this is a large fraction of the people in the world who would use shell model codes. That's just the reality of it. But Heiko has comment.
But I mean, I very much want to echo what Patrick said there, right? So it is we have complex detectors and we have dedicated staff at laboratories that know how to handle these detectors and maybe when to whack them with a hammer at the right moment, right? For many of the codes that we are using, we don't have that. So the people, like for instance, with Nucor, Gustav and his folks being around, that's a huge boon, right, for a couple of cluster codes. And that has measurable impact on output productivity, right? So plus there is the thing like, okay, a lot of the hands-on work on our codes, let's not kid ourselves, is done by graduate students and postdocs, because it's not people like us anymore or the senior people who are working on the codes. And then there's a very real risk that as soon as these people graduate or take a job in the industry, knowledge on what to do with this code or how to extend it is lost, and maybe lost forever, and someone else has to start all the way back from scratch. So, and this is only going to get more important also in experiment. I mean, now there's a lot of use of machine learning for signal discrimination and stuff, right? So the software reading out experimental detectors is going to get more complex as well. So the research software engineering need is not just on the theory side, it's also on the experimental side. And I know it feels like this is a recurring theme. I heard also from colleagues, this pops up every 10 years. And then there is the question of funding, et cetera, et cetera. But I guess maybe it takes even just again another attempt, a more concentrated push, given that we now see this broader need and how everyone is kind of talking about AI, ML, how important it is. Maybe we can piggyback on that and actually say, no, see, now the need is even greater for dedicated people like that. And then maybe it's, sorry, ramble. So maybe then it's not someone who has to go and get their own grant funding, you know, maybe then it has to be kind of like a staff position, or there has to be funding categories that someone in a group can apply for to ensure like somewhat longer term research software support. Because at the moment we don't have it. I mean, chemistry and other fields have it. We don't. And I think we're seeing some impact already, and it's only going to get worse as software gets more complex.
I want to add to this point a little bit. One of the things when you look at code that's developed by somebody who is trained in writing code versus us, is you see a lot more modularity and templating to where if you want to add GPs to your code, it's been abstracted away enough to this point to where it's not much work for that code expert to do. But we tend to sort of write our codes to the current machine we have, ignoring this fact. And I think this is actually where we need these people who are trained in code development to do this, and we can guide them in the physics and the math, but they are the experts of the software engineering, and that's what's lacking in a lot of what we do. And by having that, then we gain this longevity of our codes that we can go through, you know, multiple HPC cycles of, 4 or 5 machines from now and not have a major rewrite of the code. But at the moment, we're not doing that or there.
I will say at San Diego State, we have a specific PhD program, what we call computational science, not computer science, computational science, which essentially is meant to address this. I always pitch it as saying, basically us physicists or domain scientists are pretty crappy at writing code. But often our experience when we go to the computer scientists and tell them we have a problem, is, oh yeah, I wrote a paper on this, here you go, my job is done. And so we train students properly in how to write code, but they do a domain science project in nuclear physics or something like this, so they can actually talk to and understand scientists. And my students have done very well. So I think this helps to fit this need. We've seen several hands.
I was just going to say that I think this sort of goes along, Alex, with what you were saying just a few minutes ago, which is that different people are good at different things. And, somehow We need people who are good at the code development and spend their time doing that so that people who maybe that's not their emphasis can do other things that they're good at. So it's
Yes, and I was saying, I was lucky to have found such a person in the right niche.
Sandra, I almost had both the hands up.
Yeah.
I wanted to say, I think probability is very important. So you don't want to rewrite your code every 5 years. If you want to write it now for GPUs, who knows what's available in 5 years. And one of the solutions that we learned from Gustav Jansen was simply to use routines that other people will work on, like BLAST routines or LAPAC routines. Those will be optimized and will be and use those as much as you can in your own code. Then basically they will be portable on the next machine because other people take care of it. Otherwise, it becomes just a rat race that you never win, but you are always behind catching up with what's coming new.
Yeah, no, I just wanted to say, maybe orthogonal to many of these thoughts is that there is also value in writing your own code from scratch. So it's true to have, it's good to have all this infrastructure, it's all of this is good. But I mean, training and learning new stuff and sometimes really require starting your own stuff. Like I learned so much in writing my own experiences that I had Steve Piper huge code, which was basically impossible to understand without him explaining to me every single line. Also because his brain worked much faster than mine. But like writing your own code from scratch, even though it's not going to be the production code, it's also important to really understand what's going on. It's like doing exercises in quantitative theory after you read the theory. You really understand it when you really understand. You think you understand it once you do exercises. If you just read the theory, it doesn't really work. So yeah, it's great to have all of this infrastructure, this engineering stuff behind, but really the physics is what we're after, right? And sometimes writing, the ideal thing is to be able to write a small code that kind of solves the problem and then go to the production code and implement what you learned. But I think it's important to step in between. Otherwise, understanding really the physics is what we're missing. I think the risk is that, yeah.
Yeah,
I'd like to echo what Alessandro is saying, and actually Kyle and I were having this discussion earlier. At the end of the day, when you write your own code, you are forced to spend time to think about the problems. You are forced to think about the layout of the problem, and in some cases, it actually helps you come up with a more efficient solution to the problem, which might not have been necessarily the case if you were to outsource it. We're in a better situation because tools like LAPAC and BLAST always existed, but as time progresses, more and more things are getting outsourced than what used to. So now it's become much more tempting to plug and play into your code. But to get to the point where you plug and play, I feel that the knowledge that you gain and the understanding that you gain from the physical problem does not only come from running the code, but from understanding its flow.
The bugs and from really letting your head.
But it's even a useful exercise for students to write their own code and then to use the BLAS or the LAPAC routine and see just how much faster that will run. No, seriously, I'm sure you've all had that experience, but they don't believe, and the students don't believe it. They don't believe it really can happen until they do it, and then you go, oh my goodness, I didn't think this was possible.
Alfredo, you have a comment? Go ahead.
Yeah, it's very interesting, but at the end of the day, we want to be the first ones to do something. And you cannot imagine that you concoct a fabulous idea of a code and get someone which is in the informatics line, etc. No, because you're a physicist and you want to solve a problem and to solve it the first. The problem, these discussions is when you consider physics as a mass production industry. And, well, I have my doubts. Obviously, if the future of nuclear physics is to deal with 10 to the 10 improbable or implausible sets of interaction, and then do all these things, then, my God, you better go to this massive engineering stuff. But I'm obviously in the past.
Okay, there's all
To
sorts of.
make
Yeah.
to make the Antoine Code, that was a complete revolution, gaining in one day 3 orders of magnitude, took Etienne Courrier just to have a special algorithmic ability without need of a massive computing backing, no? So it's a complicated stuff. I am not sure. I don't say that. And it was a very clever comment, is that if you introduce that in the field, when are you going and where to get them a professorship at the university?
Right, well, thank you, Alfredo. Let's hand it off to Chloe.
Yeah, but I'm agreeing partly with what you said, Alfredo. So I think in general, there is the idea of getting bigger model space, having cleaner code, optimizing for modern infrastructure, which is really a part of the field. And some people really need to have a good relationship with computer. It's probably not especially in my case. But I think the future of nuclear structure also has to raise the question of what the physics is backing. It's not only about getting bigger, but getting faster computer and better memory allocation. I don't even all the issue that comes up that people have to deal with within this audience. And I think that when we're seeing that nuclear structure is actually a really impressive field in the sense that many nuclei are pretty much under control. Well, more usually when you use phenomenology, it seems to still beat ab initio methods, but still the progress are very fast. But there are still some conceptual questions that are not solved by any of the problems, any of the method of choice. And clearly for people who know me in this audience, it will not be surprising, but there is clearly an inconsistency in the way we treat structure and reaction. And from this, I think what Volia showed today is actually one way to go. We need to actually understand these threshold effects. And we need to understand this now because outside of it being now exploring the drip line and all this neutron-rich system where the separation energy go down, your state goes closer to the threshold, and you have all these new effects appearing, is not only in the US, it's what FAIR is going to be about, it's what RICAN is going to be about. So in the world, we are putting billions on facilities that are exploring nuclei close to the drip line, but we still don't know how to actually embed, well, some people know better than others, but at least it's not as pushed as I think it should be to embed this continuum degrees of freedom within modern nuclear structure calculation. And yeah, so I think that was one of the, it echoes one of the comment that Vitek made today about Oxygen 28. But so yeah, I agree that not everything is about bigger model space. Personally, I don't think I would have done nuclear physics if I was sold a topic like that.
No, but my point is, who does the first jump? Huh?
I think that maybe
For the codes to be really adapted to our interests, you need to have someone which is fighting with that.
So I think that
Could be improved by professionals in programming, but you should rely we should rely in ourselves for at least for the first step.
Right, thank you, Alfredo. Yeah, so there are lots of problems that we need to solve. Some of them require massive resources just to do the first calculation of some state. That's very difficult. But then there are other problems where you don't need massive resources. Being fast, being intuitive is the key to solving that problem. And so I see both sides to that. But now we have to go to dinner pretty soon. So I would like to thank this panel, first of all. To thank everybody who participated in the symposium. Thank you so much. And there will be 2 vans parked out there going to the Kellogg Center. Big 10C is the room for dinner. It'll start at 6 o'clock. Come on in. Okay. My wife will be playing the piano, hopefully. She'll be. So, yeah.
When do the buses leave?
So the vans will be.
Please follow me. They said,
Yeah, he's one of the drivers. There are many cars also driving.
So that's what's happening.
Somebody
Also
driving. Thank you.
Salaries are significantly less than actually. See now. I just said that.
Well, it's good at, I wanna know what you got.
You're like pointing at me. No, it's my place too, but it's fine.
Your point, the guy had, he had the books on this.
Is there an the computer? I don't see her on Slack. I don't see her in person.
I think there he is.
You should probably, well, let's ask them what we're.
Yeah, I'll be back in December.
No hurry, no hurry.
Yeah, they're doing. I see you, but yeah, Cleveland, Randall,
Ran around the corner to the restroom.
I have some that work. It has to do with, there's some.
Enjoy the dinner.
Thank you, Fredo.
Thanks, thanks for joining.
Yeah, I appreciate your contribution. Great talk, Fredo.
In general, it's a good idea, right? Amount of parking there, right?
Yeah, but if you have.
Kellogg could be fine.
But I was trying to, so that like.